All right, the recording has been started. Welcome, everyone. I appreciate you joining us tonight. I don't know how many people are on spring break. I know that my team is coming back from spring break starting tomorrow. It's always such a weird time between if you're doing two competitions and you have spring break in the middle. It's a weird time to take a break and then get back in the swing of things. But hopefully it goes well for everybody. Tonight's call, we're going to be talking about PID. I would assume tuning, control. Sam, you can give us an overview. But Sam, is it Wieselman? Is that how you pronounce it?
Yep, that's right. Yep, nailed it.
So Sam is going to give our presentation tonight. And take it away, Sam. The floor is yours.
All right, cool. Yeah, so as I kind of said earlier, if anyone has any questions at any point, go ahead. I tried to kind of lay this out as kind of some level of theory, some practical things, some just kind of general advice. And so there should be a mixture of it. It is definitely kind of a crash course. It's, you can get your PhD in control theory. So I remember taking multiple classes of it in college and stuff. So we'll do our best to cover it in an hour and a half here. So cool, yeah, I'm Sam Wieselman, lead mentor in 2847 out of Fairmont. And so there's a couple students from our team here too that I might throw some questions to too. So yeah, I'll go ahead and start. So yeah, high level, just kind of controlling FRC mechanisms. And I just have to, okay. Sorry, getting used to the presenting thing here. Okay, so really there's a ton of different mechanisms in FRC that we can control. So we go from the drive-based speed wheels, a turret, really a couple categories of them. And even though you use PID for all of them, there are some but there's some subtle differences between them. And so I just have a couple different kinds here. So positional rotation. So those are things that need to rotate. So it could be your entire drive base needs to rotate. If you need to turn one of the your swerve motor, or you have a turret on your robot. Another kind is positional, but with fighting gravity. So you think a lot of teams we've seen have big long arms that you've got to swing through space, or even just deploying an intake. And so even though there's simple positioning, also throwing gravity in there can be a bit of a loop. You also have your linear mechanism, so an elevator that goes straight up and down, or a kind of climber. And so very similar, except gravity is much simpler in those cases because it's not rotational, it's just straight up and down. And then kind of the last set of just pure velocity control, so trying to control how fast your drivetrain's spinning, how fast the flywheel's going, how fast the conveyor is going. So those are just kind of a couple different examples of things we control. Let's see if I can, yes. So there's lots of different ways to control things. And if you just type control theory into Google, you'll see there's a bunch of different other methods. For what we do in FRC, PID, which is a feedback methodology plus feed forward, basically can cover everything we need to do. I know some very advanced teams do other things, but it really doesn't seem necessary. I haven't really run into it. I haven't talked to a lot of teams, at least around here, that have kind of run into that. So for the most part, we're going to be talking PID with feed forward. And so kind of wanted to highlight this feed forward term here, usually called F, and you'll see F or you'll see KF when anyone who's dove into the code on this. And really all feed forward is saying is, given I want my mechanism to do something, I know I have to give it at least this much voltage or duty cycle. So in the case of, let's say the case of a flywheel, I know I want it to go 80% speed. I can probably give it about 80% or maybe 75% voltage. I know I'll get pretty close. And so all this is saying is, I know what state my robot's currently in, and I know what I want to do. Therefore, give it this much power, usually in the form of voltage. And so that's generally a simpler, kind of a simpler thing. The harder one, it comes down to the feedback control, or what we call the PID, and I'll dig into that. But really what that's saying is, given an output, I need to adjust my input. So let's say I'm running that flywheel. I want to set that flywheel at 80% speed. I'm already giving it 75% of the voltage. We're going to measure it, and we're going to say, oh, we're this much off. We're off a couple rotations per second. Let's give it more voltage to get up there. Or we're going too fast. Let's back off. And so here's kind of a visual representation of that, where and this is used in PID and control theory a lot. I'm not sure if I like the terminology, but generally your mechanism is called a plant. And so that little U of t there is saying, given this much input, a voltage. So let's say I give voltage to the flywheel, and then y of t would be the speed that comes out of it. And so in this case, we've got our feed forward saying, given our input, here's how much, and our feedback, which is saying, really looking at the error, the difference between what we want and what we're doing, and saying, we're going to look at that error and we're going to kind of apply more or less power, really. That's kind of a high level of what we're trying to do. And I'll dive into some of these acronyms and these, what some of these terms mean. So feed forward, pretty much most of the modern FRC controllers really do have a term in there called KF. KF is really used more for, in FRC it's really used, kind of the two main ones are for motion profiling and for velocity. And so in this case, just have a really simple, it's really generally a simple formula where we're saying, given I would like to go 70%, take that times my KF, and that's how much voltage we should apply. And so, yeah, the simple one is usually in drivetrains and flywheels, just saying I want 80% speed, give it 80% voltage. And the nice thing about this is, in general, with feed forward, if you give it enough feed forward, feedback has to do less. And feedback's kind of the tricky part. Anyone in here who's tried to kind of use it knows that's kind of the tricky dynamic part. And so in general, we want to maximize the amount of feed forward we're using. Feed forward is also more predictable generally. So the other thing is, if anyone's come across this term arbitrary feed forward, that's really saying that, let me back up here. On a lot of our motor controllers, we've got this KF term, and you can generally set it in the settings. And so that's kind of this thing I keep alluding to of a multiplier, saying, given my set point, here's how much I want to apply. The arbitrary feed forward lets you add even more voltage on top of anything that's already being calculated. So I'll dive into that a little bit more later, but that's really saying I'm doing some of the feedback or the feed forward control in my RoboRio, and I want to give the motor controller more information because the motor controller really only generally knows about the motor. The other thing is that KF on at least all the FRC controllers we've worked with only applies for velocity and motion profiling. So the Motion Magic in Phoenix, and Smart Motion, I believe it's called in the Rev stuff. And so if you're adding KF to your positional control, it won't do anything. And it's kind of a subtle thing in the documentation, so don't expect it to do anything. And yeah, in general, the higher your feed forward is, the more accurately that is tuned in, the easier it is to get your feedback working, because your feedback is essentially being asked to do less. And feed forward is really looking forward. So you're saying, I know the state of my robot and I know what I want to do. And that can be really helpful. Really helpful in making if you know what you want it to do, getting it 80% of the way there, 95% of the way there, without having to look at sensors or any kind of feedback mechanisms. So then feedback, I'm just going to kind of break these down into sections. This is where our PID comes from. PID, so the P term, this proportional constant here, really all this is saying is, given my set point, subtract my current value, and I'm going to multiply that by Kp, and that's how much extra voltage is going to be applied. So if I just break that down really fast, let's say I have a Kp of 10, and let's say I'm trying to run my flywheel at 80% speed. What I'm really, I request 80%. My sensor sees that I'm only at 78% speed. It's going to take that 80 minus 2%, and it's going to multiply it by my 10, and that's how much extra voltage it's going to apply. And so this is going to vary based on control system to control system, but it's a really helpful thing. It's a really helpful sanity check to try to understand what the units of your KP are when you're doing this. Sometimes they're kind of funky, but they can also really help you understand if you're on the right track or not. And so in the case of my flywheel, I'm really thinking I want to think about in the terms of, if I'm off 2 rotations per second, how much voltage should I have to give it to get it back up to speed? Should it be 0.5 volts? Should it be 0.1 volt? Should it be 10? And that can at least tell you if some of your constants are in the right kind of frame of reference. I've seen a lot of I've seen teams with numbers that are very, very small or very, very large. And I think if the units were maybe more understood or kind of dug into what they mean, we can really kind of narrow down on what's an acceptable value. And so just kind of understanding, trying your best to understand what this set or kind of what this error term is and what units this is, and that therefore what terms your KP is in and how that translates to voltage. Are there any questions on that? I know that was kind of fast, but. And so this is called P because it's proportional. So the amount, really the best way to think about this is the more wrong you are, the further you are away from what you're trying to be, the more power it's going to give it. And it's proportional. So it's proportional to your error. And in FRC, really, this is like the 90%, 95%, maybe even 98% term. This is really what you need to focus on. So the other two terms, the I and the D, I suppose I split the order here, but the derivative term and the integral term. And so what KD is doing, it's very similar, where we're finding the error in the same way. We're finding the gap between our output and what we want it to be. But in the case of derivative, it's really saying what's the change in error and applying voltage based on the change in error. So if our error is getting, so really what this is saying is if our error is rapidly changing, KD is going to apply a lot of voltage to try to cancel that. And so potentially maybe have some experience in having mechanisms that oscillate, or when you're really close to your set point. So you're saying, I want 80%, I want you to spin at 80 RPM. When it gets about to 79, it just bounces between 79 and 81. This is a good place to use that derivative term because it's really saying the error is rapidly changing and it's going to cancel that rapid error change. And the last one is the integral term. And in general, you're just going to hear me say, don't use it. And I think it's going to be a kind of a running theme of try your best not to use it. If you can avoid it, don't use it. And really what this one is saying, it's saying the sum of your error over time. And so if you're far away for a long time, it's going to kick in more and it's going to apply voltage or apply power to try to get rid of that error. And so what this is really useful for is if you have a mechanism that, let's say you're trying to set it to 80 RPM and it hits 70, 75 or 79.5 and it's sitting at that 79.5 for a long time. Over time, because we're summing the error, we're adding it all together. Eventually KI is going to take over and say, okay, it's been an error for a long time. I'm going to apply more voltage. The only problem with this is because there's a time term involved in it. It's really, really easy to get unstable. And so what can happen is, let's say that you're at 79.5 and then it overshoots to 80.5. Well, now you have error that's also adding up over time, and you can get this wild instability where things get kind of nasty fast. And anyone who's played with the I term, generally it's very, very small compared to your KD and your KP. And if you set it high, you can very easily get some instability. So that's something worth thinking about. So any kind of high level questions on what those terms are, just kind of what we're talking about or referring to. I know it's, like I said, you can get a PhD in this stuff, but it's kind of a high level anyway. If not, we'll keep going here. And so here's just some advanced concepts. The one is gain scheduling. And so gain scheduling is really saying that it's really useful if you have a mechanism that you almost need two sets of PID for. You need one set when you're really close to your set point, and you need another one that's really far away. I won't dig into that too much. I don't think we've ever had to use it, but I know teams have. The other thing is just knowing that PID is really, even though it uses time, it kind of it's modeled in a way that makes assumptions that you're able to know what your current value is immediately, which really isn't the case in a lot of the systems we use. And so let's say you have an ARM with an external encoder on it that's connected over CAN. CAN has some lag, the encoder is going to have some lag, your RoboRio has some lag. And instead of instantaneously reading that sensor, you're actually reading it maybe 20, maybe 30, maybe 50 milliseconds later. And generally, if you're trying to go slow, it doesn't matter too much. But if you're trying to go fast, if you're trying to really go fast and get non-oscillate, really stable, crisp systems, you'll start running into that. The other one that is really laggy that a lot of teams I'm sure have run into is when you're reading a vision target, because the camera has to take a picture, has to process the picture, has to send it over the network, RoboRio has to read it. And so even aligning to a target, a lot of times you'll find that you can't quite, it's very challenging to align to a target using PID as fast as you'd like to, because there's this inherent lag effect. And really PID does not take into account that lag. There's other control forms that do, but there's also ways to kind of take care of that with PID as well to try to do your best. So, and the last one, kind of an advanced thing, is called motion profiling. And this is really saying, rather than just, we'll kind of rolling the clock back. Let's say I have an arm that, let's do an elevator. I have an elevator that I want to run from the top to the bottom. With that proportional term, it's going to give it the most power at the bottom, and the closer I get, it's going to actually back off on that power. And so what you'll see if you have like really long elevators or tall things, you'll see when it takes out of the bottom, it takes off like a rocket, and as it gets closer, it kind of stalls and slows down. And generally, for a lot of mechanisms, that's not a big deal. But if it is, we start digging into what's called motion profiling, where we can actually control it out of the bottom, saying accelerate slowly out of the bottom, don't jerk hard on the mechanism and give it full power. This top part, or kind of cruise at a speed, and then when you get close, kind of decelerate into it. And so here's kind of a trapezoidal profile. So really, this is your mechanism. Its speed is getting faster, faster, faster. We hit a speed that we want to kind of cruise at, and then we want to decelerate. And so these terms are, the height of the trapezoid is the cruise velocity, and the slope is the cruise acceleration. So these are kind of some terms I'll throw around a little bit, or I won't dig too deep into it, but that's kind of what motion profiling is at a high level. So I'll kind of keep going here. And then also in your mechanisms, there's a bunch of mechanical considerations. A big one you see a lot is friction. So if the system friction it's not that it's impossible to tackle friction, but the hard thing is if you have friction that isn't uniform in the system. So like, let's say you're turning an arm and you've got a sticky spot, or for whatever reason you've got burrs on the thing. Any reason there's sticky spots, your control system is going to struggle with that, because it's assuming when it applies a voltage, it's going to move. And if you have kind of basically a variable voltage that's required to move it through its range of motion, you're going to have problems generally. Another thing is anytime you can counterbalance an arm or an elevator to try to get rid of those gravitational terms, you're going to be really happy. It's really, some of this is just doing the mechanical work ahead of time to make your software have to do less and your motors have to do less. And the last one, I'll dive deeper into this later, is minimizing backlash in the system. And so I have some gears here. So in gears inherently have to have, well, I guess I'll back up. Backlash is really, what we're saying is the motor moves. So the rotor, the actual part of the motor that sticks out, will move, but your mechanical system downstream will not move. And all gears inherently have to have some backlash, otherwise they can't change directions or even really line up. So there's always some, but the less, the better. And if you really think about why this messes up a control system, let's say the motor let's really exaggerate it. Let's say the motor spins 10 times and your arm doesn't move at all. Well, that's really going to confuse it when it thinks it just moved 10 times and you have a sensor on the other side, or you have a sensor seeing that the motor moved, but the mechanical system didn't move. And so really we're trying to, when we say minimize backlash, what we're really trying to do is say the motor is directly coupled to the output mechanism. When the motor moves, the output mechanism always moves, whatever we're trying to move, whether it's an elevator, an arm, a drivetrain. But we're also trying to balance this. There has to be some backlash, especially in gears, there has to be some. But I can dig deeper into the details on minimizing that. But anyone who's tried to tune a system with a lot of backlash in it has probably seen maybe some amount of instability or some amount of kind of wobble, or maybe some confusing things when you change directions. So any questions so far on anything? I guess that's kind of a crash course, but okay, keep going. This one I really wanted to emphasize is having good instrumentation and measuring is really helpful when we're working through these processes. And so honestly, if you really want to get if you want to really build this skill up on your team, a really great place to start and a really approachable way to start is just get used to looking at, figuring out how to look at graphs of your mechanisms over time. So I have a couple things that are kind of useful to see. What you're trying to tell your mechanism to do, the set point. the actual position of it, the error, so the difference between your set point and your position, potentially the voltage and the amperage of those systems too. There's a lot of different ways of getting this done. I'd be happy to dive into them too, but just directly logging on the Rio and then pulling those log files out and looking at them in Excel. There's some tools. Advantage Scope's a really great one. If you're using the Phoenix Tuner tool, there's a way to look at signals on there that we've used a lot. And you can even, this one is maybe not quite as good, but there are different times when it's nice to be able to look at the actual range of motion on a camera and kind of see if you can see some acceleration or some jumping or some wobbling in there. But this is really important because I've seen a lot of people struggle with PID, and really the underlying thing was that they didn't really understand what their set point was. Or let's say you have an arm and it's moving, the sensor's flipped backwards so that you're trying to move it from 0 degrees to 90 degrees, but as you're moving, the sensor is actually going from 0 to -90. And so being able to graph these signals and look at them will really help you kind of track what the system's doing. And when you're putting in these magic constants to try to tune them in, you actually can see how they affect the outlying system rather than trying to guess and check and having questions when there's instability. So I would say this is a really great place to start, is just kind of learning how to instrument and watch these values over time. And it should be a lot more approachable than just trying to control something right out of the gate. I'll keep going here. And so this is just some high level things when you're trying to tune a PID and trying to find your right values, your right constant values. The first thing is verify that your position and velocity sensors are all working properly. And this can be as simple as pulling up one of those graphical tools or recording tools and taking a wheel and turning it the way you think it should. Say you have a flywheel, turn it by hand and make sure that it's sensing velocity, it's sensing position. When you move an arm through your range of motion, make sure that -50 is -50, 100 is 100. And getting all of these wired up correctly so that your control system is actually seeing what you think it should see. A couple other things. The D term, the KD term, is generally not needed. The best time to add it is when you're seeing a mechanism move through space and it's overshooting very slightly. So you say move from 50 degrees to 60, it moves, but then maybe it jumps up to 62 for a moment and then flops back to 60. That's a great time where you can try throwing some D in there and seeing if it takes it out a little bit. And then also if you have any what are called steady state oscillations. So let's say you get to 60 and you notice it's just kind of fluttering between 59.5 and 60.5. You kind of have this 1 degree flux. It's a good time to try it. In general, the I term is not, just try to avoid it because it's really complex, and there are times too where you'll add it and it'll seem to work, but then it can also kind of introduce, I don't want to say like phantom errors, but it can also introduce errors that, because it's based on time, if a mechanism is moving through space and it bumps something on the field and slows down, all of a sudden that term gets really big, or you run into something you shouldn't, or you're trying something in the shop and you have a sticky spot in something. Because it's time dependent, if time ever changes while you're moving through your motion, the KI will start kind of adding some instability. And so one of the reasons a lot of people will add the I is because when let's say you're trying to move your arm to 80 degrees and you find that you're 79 degrees and you're a degree short all the time. So you add the I in to try to get that last 1 degree. Something I might suggest is just moving the set points to compensate for that. So rather than making your system more complex and dynamic, you just adjust it and say, well, I guess 81 is the new 80. And that can be a little, if you're very CAD driven and math driven, that can be a little, you have this fudge factor in there. But it can be easier than trying to make your control system more dynamic. The other thing is, if you're having problems controlling things with just your KP and you're not getting close, really try to resist the urge to throw some KD or KI at it and seeing what happens. It almost never will make it better, and you really want to get some stability with your KP first. The other thing we've seen problems with is some of the motors will have defaults. So they'll say, and it's useful for teleop, and so this is kind of a trade-off a little bit maybe, or it's useful when you're just like controlling a motor with a joystick, is it'll say, unless you're giving me, I believe the Falcon's even default to, unless you're giving it 4% voltage, it will apply 0. It won't apply anything to the motor shaft. And I'll ran into this where we had a mechanism that we had our arm last year. And there was a lot of times it was falling below that 4%. And so the arm would kind of drift down, and then the 4% would kick back in, and it would turn on. And so instead of having this nice stiff system, it ended up kind of turning on and off over. And it drove us crazy until we figured out, oh, there's just a setting there. If you're doing any kind of PID that's not using the motor controllers on the RoboRio, speeding up the signal frequency on CAN can help a lot too. That's just something, essentially, as I mentioned, that the signals that come across CAN have an inherent delay in them. There's a big lag in there, not big, but 10, 20 millisecond lag in there. If you're sending the signal more often, your RoboRio is doing its calculations with more up-to-date things. This is kind of those time. It's really just trying to reduce that time lag. Another thing, start slow and really try to get the mechanism to drive to your set point, and then try to get it to go faster. It's really helpful to, rather than trying to get it to snap right away, and really sometimes really actually do some cycles with the robot and make sure that, like, even if it looks slow while you're watching it, does it actually affect your cycle time? Is it worth trying to tune out that last 10% speed, that last 20%? And you can also really venture into that unstable category really fast. And so start slow. I really recommend starting slow and kind of running with it slow for a while, and then seeing if you can speed it up once you get comfortable with it. We also like to, when you're doing the tuning, make big changes in your KP and kind of narrow down later. And so it can be a huge waste of time to start with a value that's way off and adding 10% to it, add 10%. I know, let's see, do we have, I was trying to see if anyone from our team is here. Looks like the person I was going to call on isn't, but we actually kind of have a habit of doubling it or adding 50% to it and seeing kind of what happens, and really trying to narrow in that way. And just so we're not adding 5% over and over and over and watching these incremental changes. And it kind of helps you understand what these terms are doing. If you make a big change and you see a big change, versus, especially if you have some instability, it can be really easy to add 5% here, 5% there, and not realize what is actually controlling the change. I guess I mentioned this before. Alignment with April tags is challenging, and sometimes you just have to go slow because of camera lag. One of the ways you can maybe help with that is turning down the resolution and cranking up the frame rate on your camera. But of course, you're going to lose distance and accuracy. And so really, that's all just kind of a big tuning experiment. And if you really want to get more accurate than that, you might have to look at a different way of tracking your position in space, rather than just looking at your tag and saying, I'm off 5 degrees, therefore adjust. And the last one that you see probably a lot of questions on is, arms are inherently the trickiest thing to control, because when an arm moves through space, or when it rotates through space, gravity does not act on it uniformly. And you can feel this in your own arm, where if you hold your arm straight out, especially if you hold like a 5-pound weight, hold your arm straight out versus holding it right above your head, you'll find that holding it straight out is much harder. And if you swing it through space, you'll see the same thing. And so it really and I kind of threw the equation here, but the gravitational force is the weight of your arm times the cosine of theta. So where theta is, your rotation in space. And so anyone who's tried to tune an arm before has maybe seen some of this nonlinearity, where there'll be parts of it where it flies up really fast and then it kind of slows down, or it speeds up and slows down, or it can't make it through certain points, but it holds other positions really well. And really, it's because PID is really designed to, like the mathematical model of PID really does not handle cosines well. But there's ways around that too that I'll probably jump into a little bit. But okay, I feel like I've been talking a lot. Is there anybody who has any questions or anything they want to loop back on that or anything? It's kind of, like I said, I'm trying to kind of high level and fast. But
Sam, are you at some point here going to talk about actual numbers, like where you would start your tuning? I don't want to ask questions if you're going to cover it later.
Yeah, I have, let's see. I will. I always talk about processes, maybe more
Okay.
like a process of how to find good numbers, really. That's kind of
Yeah.
where I'm going.
I
Yeah.
think, yeah, where I hear students, and honestly, I'm not good at PID,
Hmm.
is understanding where do we start, and the answer to that is usually, well, what did we do last year, or I found some sample code, let's use that number, and
Right.
not understanding what those numbers mean make it challenging. I get the concept of start with a number and then increment by 50% or double it or something.
Yep.
Where to start is where I think we always struggle.
Okay, cool. Yeah, I've got some examples of that. And if there's like a mechanism we can talk about, I can maybe kind of jump into that. I think the tricky part on the numbers is that in FRC, all the motor controllers do it a little differently as far as like what the units are of the numbers, what those KPs mean and the different numbers mean. And so it can be tricky in the sense like if you're on Rev, start with this. If you're on a Falcon with this, start with that. So, but I'll at least jump into that some. I guess just some system design things. The Roborio is a little slow. Not slow, but just keep in mind that command-based robots 20 milliseconds. Um, using the integrated motor controller when possible, so the actual control system that's on the motor. I believe those run at under a millisecond, so you're really getting 20% or 20%, 20 times faster control loops. And really, that's where that comes into play is what I was talking about with the difference between what's really happening and what the motor controller thinks is happening. Because it's running so much faster, it knows the true state of the world, and therefore it can react faster. Whereas your Rio is kind of reacting to the past. Sensor placement, it can be nice to have your sensors as near to the output as possible. For similar reasons with the backlash and differences between motors and mechanical things. The other thing is your motor needs some headroom to run control systems well. And so really what I kind of threw here is like, if you're using high voltage to move the mechanism, you're going to struggle to control it well. And I know there's probably people have had different experiences with this. Maybe this 10 to 15% motor, voltage or duty cycle to hold it is too low. Maybe that's kind of a high standard, but and maybe it's not quite necessary. But when you start getting into the 60, 70, 80%, if that's all it takes just to hold the mechanism in place, you don't have a lot of room to move it very fast. You need to accelerate it, you need to slow it down, you need to respond to errors, you need to respond to driving around the field and ramming things. And so that's a big one there. And so that might be a back to the drawing board. You might need to add more, change your gear ratio, change something mechanically on that, lighten your mechanism. And the last one I just want to talk, or one of these is beware of changing dynamics. So I know in 2023 we dealt with, we built a very, very light arm. I can't remember exactly what the weight was, but somewhere around 7 or 8 pounds. Well, you threw a 2-pound cone on the very end of that, and then you extended that arm, and all of a sudden you're moving this cone, which has more of the impact on your arm than really the weight of the arm itself does. And so something to think about as, if you have an elevator and you're lifting a 10-pound game piece, you might have to have two different control sets, one with a game piece and one without. So it's something to think forward about when you're doing your design. And so I want to jump into a couple kind of some calibration techniques that we've been doing. Kind of learn these from other teams and kind of working backwards. And so this one is trying to get solve the swerve drive. Anyone who's doing a swerve drive, the actual wheels on the drive have a control system on them to make sure they're actually running at the speed they're on. And the more accurate that speed is, the better the faster you'll be able to go when you're doing your auto pathing and auto. Just the more crisp it's going to feel to your driver when you're trying to change directions and speed, the better you're going to be able to rotate while driving. And so it's kind of just a process to kind of narrow that in. And so really, Scott, I don't have the best example of like numbers to start at, but I kind of have like a set everything to 0 and change these one number at a time, if that makes sense. So in this case, if your modules let you lock them in place so that they can't rotate, so they can only go straight, use Path Planner, or if you have some other way to drive in a very long straight line and make it as long as you can, set all of your PID to 0. So both on your path planning, any kind of path following, and also on your wheels, set all the PID and the forward to 0. And then on your path, bring the acceleration way down. So so that it's not doing a really hard and heavy acceleration, and find a typical velocity you want to drive at, or a pretty one you'd like to especially run your autos in. And so in this case, you're gonna run that path over and over and bump up your KF, which is your feed forward term, until the robot follows that path pretty closely. And remember that feed forward term is the one saying the motors want to rotate at 80%, or if the motors want to rotate at 80%, how much voltage should I give them multiplied? So, or let's do 100% really. Well, it's a multiplier by your desired speed. And so what this is going to let you do is it's going to let you isolate your feed forward and saying, as you're driving down this long path, you're going to accelerate very slowly, and then you're going to hit this top speed of, let's say it's 70%. And you're going to drive at that speed for a long time. It'll let you kind of narrow in on what that KF is. And so this basically involves running the robot down the path, watching how closely it follows that path. So does it hit the end point of your path, bringing it back and doing that. And like I said, I recommend making the big jumps and then narrowing in until you're around that 10%, maybe 15. I don't have the best number, but somewhere in there. And then you can crank your acceleration up to a normal value. And then you're going to want, that's acceleration on the path. So accelerate the way you'd like to. And then you're going to add your KP back to the drive wheel until you follow that path pretty darn closely. Like we're talking 5%. And so what that KP will do is that will, your feed forward's done a ton of the work. It's done 90% of the work. You're going to add this KP term back on your wheel speed. This is on your wheels to get them that last bit so they follow the speed really well. And then you're going to add the KP back on your path planner to really try to get rid of that last bit of error. And so each one of these is kind of a tuning step to see if you can get to this 5% and see if you can get down to this last where there's no error. And one of the things that's also kind of tricky is on your swerve drive, it's going to depend on how heavy you are and what your gear ratios are of how hard, how much voltage you have to get them to hit your desired speed. And so really, if you end up swapping your gear ratios or adding a lot of weight to your robot, you kind of have to redo this. And I say a lot of weight. Honestly, if you added 10 or 15%, that's probably kind of where you're getting there. 10, 15, 20 pounds, that's probably where you're kind of getting there. And then swapping the gear ratios too. But using this, we've had decent luck.
Sam, when you say follow the path closely, plus or minus 10%, 5%, what is this 10%? When you say follow the path closely, I'm thinking that you're hitting your X and your Y, but I'm confused on what that means when you're adding 10 plus or minus 10%. Is it not the points? Is it something else? Yeah,
sorry. So you're driving in a long straight line, and let's say it's a 50-foot line. Mm-hmm. And so really when you run the whole path, you're going to want to try to, and really maybe 10% is too wide, but you're going to want to finish within, this is a 50-foot path within 5 feet of that endpoint consistently.
Oh, so it is finishing on the line, basically.
Yes.
Getting within, most people I think probably have a goal of, I want to be plus or minus a couple of inches, maybe not over 50 feet, but on what is an auto today? Most autos are going to be, you're going to be driving 20 feet before you change direction, something like that.
Right. Yep.
So you want to hit that within an inch or two, I suppose, for a lot of people. So when you say plus or minus 5%, you're really talking about your kind of end point.
Right. Yep. And when we do this, we actually lay out the tape measures and make sure that also Path Planner agrees with what we're doing too. So we think we drew a 50-foot line, and Path Planner doesn't actually drive 50. Kind of that business too. But
okay. And then I was thinking that F was controlling your acceleration, but then on number 6, you're talking about changing acceleration. So is the F value, is that affecting your acceleration?
Yeah, so on your motor controller, or Path Planner accelerates you, right?
Okay. Oh, okay.
Yeah, so you're changing your velocity. Velocity is telling your swerve module to increase its speed, and that's all proportional to KF. And so Path Planner doesn't use an acceleration term at all. There is acceleration, but it doesn't tell you. Sorry, I'm getting kind of twisted here. So Path Planner always controls your robot's velocity, and therefore you accelerate that way. But it never tells your module you're accelerating, add more voltage. And so, the effect of this really is really you want to be able to you want to follow the speeds that Path Planner has, without worrying that can my robot keep up with these hard accelerations. That kind of comes later. That's where you need the KP and the
Okay.
if that makes sense. Maybe I should restate that better. Really, KF is just making sure your module is spinning. Its velocity is spinning at the velocity path planner is telling it to. And so if we set the acceleration really low, we've kind of taken acceleration out of the equation, so that when the robot accelerates really hard, we don't have to worry about that too much. Because if you play with path planner, you'll kind of find that at some point there's some acceleration you just cannot hit, and you'll start to lag the path really hard. And so we kind of want to take that out of the equation, basically.
Okay.
So that's kind of one. The other one I see a lot of is arms, and so I'll dive into the motion magic, which is kind of the motion profiling a little bit. And so the same thing on this one, you want to set all of your PID and your feed forwards to 0. And I'll have code with this one too. The big trick on this one for arms is it's really nice to set your arms, if you're tracking degrees in your code, having 0 be your arm, or your arm should be horizontal, and set that to your 0 degrees. And so everything can be referenced to that. And kind of the beauty of that is now that gravity will act on your arm with cosine. And so if you're at 60 degrees, it's cosine of 60 degrees, and that's how hard gravity is pulling on it. If you're straight up and down, the cosine of 90 is 0, and so gravity is not pulling on the arm at all. And so that's kind of one of the tricks is when you're doing PIDF with an arm, try to set your 0 to horizontal so you can use cosine. Here I said pick reasonable cruise velocities and accelerations. That kind of varies based on what kind of gear ratio you have for your arm. But if you really want to try to get from your start point to your set point, let's say you want to move 90 degrees in 3 seconds. Well, that means that you're going to have to probably your cruise velocity, your max speed is probably going to have to be, that basically 33 degrees a second. And so you need to convert that into, 33 degrees per second into kind of the motor controller units. And I guess that's kind of where some of the numbers get hard, because all the motor controllers are a little different, and depending on like where your numbers come from. And that's kind of where the instrumentation comes in really handy, where you can actually grab the arm, move it 90 degrees, and see it. What does my control system think that is? Is that 90 degrees here? Is that 180 motor ticks? Is that 3,000 motor ticks? So there's some conversion factors in there. But yeah, finding a reasonable cruise velocity, we've kind of found with acceleration that is, if you get from a dead stop to your max speed in like around half a second to a third of a second, it doesn't seem to break things. It seems to go pretty acceptable. And so really you'll end up kind of just taking your cruise velocity and more or less tripling it. And that seems to kind of do that. And then the next thing you want to do is hold your arm out vertically or horizontally and find how much voltage it takes to hold it there. And what that's saying is that's the maximum amount of voltage required to hold the arm up when it's in its worst case scenario. So it's kind of the scenario I was talking about, where you have a 10-pound weight in your arm and you're holding it straight out. How much force does that take? And so similar to our cosine term, so the cosine of 0 degrees is 1. And so we kind of have this relationship where we know how much voltage it takes to hold the arm straight out. And as we move it through space, we know we can actually mathematically figure out how much voltage we need to cancel out gravity. And so that's really our whole goal here, is to cancel gravity with this kg term. It's kind of the gravity constant. Number 5, I'd call optional, is finding if you have a lot of friction in the arm. So if you have like a 300-to-1 gear ratio or 400-to-1, a high one, you might have a lot of friction. So you can get rid of friction in that way by putting the arm completely vertical and figuring out how much voltage it takes to move it just a tiny bit. And the second it starts moving, that's how much voltage it requires to cancel out friction. And I have some code on this in the next slide. So you can actually use these terms through the arbitrary feed forward of the motor. And so the motor controllers have this term called arbitrary feed forward, where it says, I have a PID on my motor controller, but I'll let the RoboRio tell me about some extra terms that I can't do. And because the motor controller can't do the kg, or it doesn't do It doesn't do gravity or friction on it necessarily. You can calculate that on your Rio, send it to your motor controller. Your controller will take that and it'll apply it also to or it'll apply it with what it's already trying to do. So essentially at this point, we've kind of canceled. So by passing these forward, we've kind of canceled gravity and friction out. And a good way to verify this is you should be able to take your arm and manually move it to 30 degrees. And then in your code, apply 30 degrees to it. And it should just pretty much hold in place because you have, you've canceled these. And once again, I'll show the code on that. And the kind of last one is because we're using motion magic, the KF term is how, or I'll look back on that, because we're using the we're using motion magic, which uses that trapezoidal profile we looked at earlier, where it's going to accelerate it, keep it at a constant velocity, and then decelerate it. The KF term is how much that represents how much voltage is required to swing the arm at a given speed. And so really, because we've canceled gravity and friction already, we should be able to tune this KF in and move our arm between two positions. And it should pretty much get to those two positions plus or minus about 10%. And so really so once we have KF kind of tuned in, really we're kind of following the path pretty well without any feedback at all. We've done no PID at all. We've just canceled gravity, we've canceled friction, and we've kind of got our feed forward going. And then the last part is adding KP until there's really just keep adding it and cranking it up until you start seeing some instability or some overshooting, and then you back it off until you don't. And what you'll kind of end up with is some pretty crisp, kind of moving through space where it accelerates, it keeps a constant speed, and then it decelerates. And so this technique is kind of important, or some of these routines are kind of important, because if you try to jump to the end here, I see a lot of teams try to jump to like step 8 at the end and have all of these terms kind of trying to tune them or pick them. And the problem is we haven't isolated our variables. And so it can be really hard where you change one thing and you don't quite understand why it affects other parts of the system. And the nice thing about motion magic is because I keep mentioning that trapezoidal profile. While you're trying to follow that trapezoid, this KP term is actually helping you follow the trapezoid. And so it lets you have a very, very high KP, which really basically makes the system very stable because it's trying to follow the trapezoid really, really hard. It's not trying to jump from the start point to the end point. It's trying to do that nice trapezoid. And so that basically, the higher the KP, the stiffer you're going to see there on the end point. So yeah, basically that's kind of what we did with our arm in 2023. We computed the gravity compensation on the Rio and applied it as an arbitrary feed forward. We actually ended up not using friction because we had almost none. It just wasn't worth kind of the work. We also ended up having 2 different PID profiles, one for a cone and one for a cube, because the cone was so much heavier. And I guess I can maybe talk about this as an advanced topic. The latest Phoenix stuff, the cross-thread electronics stuff, will actually let you do all of this math on the motor controller. And so essentially what I've done here is, what we ended up doing really was, so this method is going to be used to move the arm from whatever position it's at to a new position. So in this case, we want to move it to 60 degrees. So we calculate where we want it to go. And then we're going to get our current position. We have to do our radians conversion, and then we're going to do the cosine of our current position. And that's, and this is how much gravity is affecting us. And then we need to convert that to our feed forward. So we're saying this constant is how heavy, it's how much voltage it requires to hold the arm straight out. And then we take it times our scalar. So let's say it takes 1 volt to hold it straight out, but we're at 60 degrees. We're going to scale it by whatever the cosine of 60 degrees is. And so we're not actually giving it full blast all the time. If the arm was totally horizontal, we would be. And so we're really saying, so here we select this PID profile. Motion magics, we set our target position, and then we add this arbitrary feed forward to offset gravity. And so in this way, we're kind of moving through space, and we're moving from one place to another and offsetting gravity so that our motor controller doesn't have to deal with it, essentially. That's kind of complex, sorry, as an example. Is there any questions on that? Or I can dive deeper into it too. I guess I'll probably add that some of this isn't necessarily, or isn't always necessary. It just depends on how fast you want to get it. Really, that's kind of the big one, is how fast you want to move it. And if you want to go faster, this is one of the ways anyway.
So since we're looking at code here, where do I start with F? Do I start with 1? Do I start with 0? How do I start? How do I pick my starting values? You said that Rev does something different than CTRE does. So how do I know? How do I know what the F represents and what the P represents?
Right. So it's really that a lot of that is going to come down to digging through like the documentation really of that motor controller and figuring out, it kind of comes from that instrumentation and measurement stuff where you're saying, what units are my measurements in, and trying to work backwards from there. And so in this, let's say what's confusing is a lot of these are in let's say that's in motor ticks, right?
Okay.
So it's in the motor ticks. So I think the Falcons have like 4,000 motor ticks.
Yep, that sounds right. Something like that.
So if we're off 3,000 motor ticks, how much voltage do we need to apply to move 3,000? Oh, sorry. Let's say our target is 4,000 motor ticks and we're at 2,000.
And when you say, you're talking about in terms of speed or position?
Let's do position.
Position. Okay.
Yep.
So let's say that we're currently sitting with an arm or something, but we're at 2,000 motor ticks, which is roughly half a rotation, and we want to get to a full rotation. Am I following correctly?
Yep, that's right. Yep.
Okay. And then you're saying how much voltage do we need to apply? But you would have, is that over time? Because as long as you can make the motor move, eventually you'll get there.
That's right.
Right. And so you're
right.
saying, and so the F would be in terms of number, it would be a voltage then in this example?
Yeah, it's really a voltage. It's a voltage times. So KP in this case is really, the units of it are the error, right? So you're off 2,000 ticks.
Okay.
So you're off 2,000 ticks. So KP is going to say 2,000 times your KP is going to be how much voltage you apply.
And if your P is 1, that's a lot of voltage. I mean,
exactly.
You're not going to be able to apply that much voltage.
That's right. Yep.
Okay. So you would need to figure out if your maximum, let's say it's your maximum voltage you wanted to apply was 10 volts.
Right. Mm-hmm.
Right. And you had to go 2,000 ticks. Maybe the right place to start though would be 10 divided by 2,000.
Yeah. Yep. I'd say that's good.
And that would be a good place to start. So that would be 200. So 1/200th. So was that 0.0? So I'll just do the math here.
Sure.
10 divided by 2,000 equals 0.005. So in this case, 0.005, it would be a good P value to start with. Because I will tell you right now that my kids will be like, well, let's try 1, and we're never going to apply 200 volts.
Yep.
And so 1 doesn't mean anything because 1 is probably in reality, 2,000 volts is this probably the same thing as 0.1 because both of them are going to be your maximum voltage that you could even apply. And so changing the value isn't going to see anything. So, okay. So that's very helpful and interesting to me because I never really understood, where to start with these numbers. And so understanding the error and what and then the P is a proportion, right? But
Yep.
another word is percentage. Is that true? You can think of it that way.
It's proportional to your error. So the more error, the more it's going to do.
Okay. All right.
And so in the same way, yeah. And so in your case where it's 1, where it should be 0.005, even if you're off 0.01%, it's still going to blast 10 volt. And that's where you're going to see some of the instability when you're that high.
Okay. And then do we have an example like this that we can use for the F of figuring out what your feed forward should be?
Yeah, really, honestly, the best one is, I wonder if I can even pull it up. You see this a lot in sample drivetrain code, but they'll calculate what your free speed should be, and they'll just say the feed forward is, let's say your max voltage is 12, right? It's just 12 divided by the max motor speed. And so in that case, it's basically saying if you're going 10%, give it 10% of your max voltage. If you're going 50%, give it 50% of your max voltage. So on velocity, that's a really, really good place to start. But you also, once again, it requires you to work backwards and find the units of that. What units are KF? What units should KF have for my motor controller and my control system?
And so that's more of, I don't want to use the word constant, but that's more of a constant for the system you're using.
Yeah.
Is that true? Where Rev, this is a good KF. Kraken's, this is a good, or so I guess it would be by the motor too, right? So for a Neo, this is a good KF. For a Kraken, this is a good KF. Is that yep. Am I understanding that correctly?
Yep, correct. Yep.
Okay. So it's voltage divided your max voltage, which you said is 12, divided by your max free speed.
Right. Yep.
And is that in ticks then, or whatever the units your encoder's counting in?
Yeah, whatever unit the encoder's counting, I believe it is ticks for the rev. I know like the base. I wonder if I can easily switch what I'm sharing. I know like the rev swerve like template code for their swerve. That's exactly what they're doing for their their wheel speed is just saying if you're going full speed, give it KF should be what. Really a good way to think about it is if you're going full speed, KF should be 100% voltage is really what they're saying, and just scale it down. 50% means 50% voltage, 40%, 40. And then they're letting that KP, that error term, get rid of the rest of it. So let's say that's not quite right? 50% voltage only gives you 48% speed. That's when error kind of kicks in and takes care of it.
So we've used Motion Magic mostly, I would say, for shooting, which you're just trying to get your wheels to a velocity, so that's sort of easy. And then for elevators, and we've done that with Falcons in the past. Krakens are too new, and we don't have an elevator this year. We're living largely in the rev world now with Neos, and so some of this Motion Magic's not available to you, so you have to do more manual type of PID stuff.
Yeah,
that's true.
That is true. They have the smart motion, but our team's never used it. But my understanding is like it can be tricky. I don't know. Maybe someone who knows more about it could speak up, but I know it doesn't work quite the same. The implementation's not quite as easy to use as Motion Magic. It's my understanding.
And is it true that when you're using these PID loops, you're focusing exclusively on volts, where volts is the thing that you care about the most when you're doing logging or advantage scope? You're always looking at the voltage for your motors?
Yeah, or duty cycle. Really, honestly, duty cycle is probably the better one. I'm more using voltage to simplify it, but the problem is, the problem with duty cycle, of course, is that if your voltage drops, so does your if you're giving it 80% duty cycle, if your motor, if your robot's battery drops at all, you're also going to apply less voltage. I know we ran into that some last year. We think that's what we're running into when we're driving full speed. We notice it not quite moving the way we'd expect. And so the newest Motion Magic stuff actually it will do volts instead of duty cycle. So it's kind of your choice. We've had a lot better success with voltage. And that way we can also kind of watch and see if we're going into that danger zone where, this is requiring 11 volts to work. Well, we know we're not going to have 11 volts all the time. We're not going to have 12 all the time. It's going to dip. Right. And so.
Yeah, especially if you're driving or if you're running shooter motors or anything like that at the same time.
Yep, especially. Yep. And I guess the last thing I will share is, so some of this work can be done with the newest kind of, what I think it's called Phoenix 6, the latest cross-the-road electronic stuff. So like all this work I'm even doing here is done on the motor controller. And we've had a lot of luck with that this year. Just it's even better than kind of doing it on the Rio. You can actually say this mechanism is this mechanism is an arm, therefore on the motor controller, if I basically all this cosine work, it will actually do on the motor controller and be even more accurate. And so we've had a lot of kind of good luck with that. It is new though, and so I don't know if we run into bugs or not. It seems there's sometimes it doesn't quite do what we'd expect, and we're not quite sure if it's us or the code, but.
Sam, is your presentation, is this a Google slide? Can you share a link to that?
Yeah, I definitely can. I don't have it right.
You can send it to me, and then I can, well, if you can throw it in the chat, that'd be great. Otherwise, you can send it to me, and I can put it in the description on YouTube.
Sure, do that. I guess, does anyone have any questions or anything specific, or it's a big topic. I know people have a lot of questions on. I'm never quite sure like which level to go at, and so I know I felt like I was kind of just talking for a long time. So if anyone has like a system, or even if they have a video or anything they want to watch or anything, I'd love to, or like a picture of a mechanism or anything, we could definitely talk about it too. There's something specific on their machine.
Well, I'll throw one out there. We have our climber arm, and our climber arm, it's a U, and it goes like this and it climbs. So we're pulling down on it, single mechanism. It's controlled by Neos on gearboxes. And no, I take that back. Let's talk about our shooter. That's the one that we have the absolute encoder on it. So we're measuring degrees of angles or radians. It doesn't matter. We're measuring absolute angle of our shooter. Mm-hmm. And it's controlled by Neos in terms of elevation. I'm almost certain that that's true. Yep. And so without all the Motion Magic stuff available to us, can you give us a starting point? We're doing a bang bang, which I don't know where that term comes from, but the bang bang idea of if I'm within 5 degrees, run up or down at this speed, and if I'm within 2 degrees, then run up or down at this speed, right? Yeah. It got us through our first regional. And it got us to a margin of accuracy that was good enough. We want that, but to be much quicker. We want to go from a 10-degree elevation or a 20-degree elevation to a 60-degree elevation. We want to do that in 1 second, and that's not where we're at today. So we want to do PID. We've never done what I would call a manual PID loop, because you're going to be doing this on the Robo Rio and not through the motor controller, since it's Neos. Yep. Where do we start? What advice do you have for using this external sensor, the angle, the rev absolute encoder, and then using that to control your PID for the Neos?
Yeah, so you're using, and you said you're using you're actually using so sorry, this is your flywheel, or this is actually the angle?
This is the elevation. So it's if you think of it as vertical aiming. So we're vertically aiming our shooter up and down.
Sure.
It's an arm.
It's an arm, yep. Yeah, so honestly where I would start is I know you can connect, I'm guessing you're maybe already connected into the Spark motor controller or whatever. There's like the ribbon cable that goes directly, or how are you reading the sensor right now?
Well, that's the sensor is, or right now it's coming into the Robo Rio because it's
Okay.
a 0 to 3.3 volts.
Okay.
So we have to change that into degrees.
Okay.
Now, we probably wouldn't need to change it into degrees. We could probably just know that, hey, at 0.8 degrees is where we're trying to go, or 0.8 volts, because it comes in an analog input and it goes from 0 to 3.3 volts.
Yeah.
And, so, but I think that the rev encoder object actually turns that into an angle. Oh, Nate's just commented here. So Nate says we can also use the absolute breakout. So we could connect it right into the SparkMax.
Yeah. So I would, if I was you, if I was whatever, I would do that, connect it directly to the SparkMax, and then maybe like a good place is really looking at like the Rev Robotics, like the swerve code, because it's really a kind of a similar deal where they're doing the same thing where they're using a rev sensor and they're controlling the rotational motor using that.
Mm-hmm.
So that's like a good baseline. But yeah, so you really want positional control on your Max, on your Spark Max, and
Okay.
and so that's maybe a good place. And of course, all the instrument, make sure you can read the sensor and everything accurately.
Right.
And then you can probably get by with just a KP on that, and just seeing if you can find a P where it kind of drives to the right. It drives to the right value.
Okay.
And then a similar thing to this right here might get you a little bit better if you can get rid of gravity.
Yeah, I feel like we probably are doing a good job with that. Our gearbox is pretty sturdy.
Okay.
Nate just commented it's 300 to 1, and we also have a spring. We also have a spring assist, so it's actually neutrally buoyant at about 30 to 40 degrees. So with no power at all, it's neutrally buoyant about halfway through the rotation.
Mm-hmm.
So we've done a pretty good job of making gravity sort of a non-factor, and then we have a high gear ratio gearbox. All right, then I will send a message to my programmers tonight that we need to rewire that and have that run directly into the SparkMax and see if we can control it that way. It's a good, good advice.
And yeah, so the big driver for that is that way you can run the control loop on the Max controller, which is going to do that 1 millisecond instead of the 20 milliseconds on the Rio, and it's just going to give you. You can get the KP way higher, which means it's just going to resist change even more. It's going to really lock in, and it should be faster.
Okay.
But I think you will run into, and I'm guessing, depending on how you tune it, you probably will run into the whole. We're telling it 20 degrees, and it consistently goes to 19.5. It's off a little bit. But if you're just doing like a tree map anyway, or a lookup table, it's just the kind of fudge factors are all built in. So.
Yeah, we are using a lookup table for all of our elevation. So we'll put the robot at 3 meters, shoot, we'll find the angle that we want, and so we'll just record that. Then we'll back it up a half a meter or a full meter and do it again. And so we figure out where we are based on the April tags, and I don't remember what our students have done there. I think that we did a really rough one with every meter. We would back up every meter and record the optimal values. But I think when they retuned it the second time, they may have done it with half meters or even less than that. So I'll check with them and see, but that's a good tip.
Yeah, and I think and it's like maybe like the good exercise to find your first KP would be figure out what the units that are coming out. And so it's all about units first, really. And it's saying, if it's off 5 degrees, what's a good expected voltage to move it? And you can kind of start backwards from there and crank it up or down.
Okay.
And the other thing is on arms, high KP, especially something like that, the higher you can get your KP without going unstable is nice. Just because, you spin up your flywheels or you shove the note through and it wants to wobble a little bit. KP will fight the wobble and make it really, really stiff, hopefully. Mm-hmm. So, or resist air really is kind of the big,
And so then with that, our F should be now. This should still be based on your maximum velocity of the rev, the Neo, right? Your KF.
So since you're doing pure positional control, you won't want KF at all. So KF is only good for motion profiling, so like the motion magic stuff, or velocity control.
Okay.
Yep.
Okay. So no F on this because we're driving to an angle, driving to a position.
Yep.
And so we're going to be focusing purely on the P and hopefully not do a D and definitely not do an I.
Yep. Yep.
Okay.
And let me know if you still have problems or if that doesn't go.
All right. Well, we'll see once we get our robot reassembled after all the damage that we had to repair from our last regional.
Oh, that looked brutal. Oh my gosh.
Yeah. Did you guys take a lot of damage at your? Okay, wait. We're gonna shift gears too much, I think, if we start down this path. Does anyone else have any questions about PID tuning?
Yeah, my team's been using a lot of the PID controller built into WPIlib. However, that does not by default have KF. Have you written your own controller for that, or is there another better controller for them to be using?
Oh boy, Can I find it in the docs right now? I believe there is one that has an F in it.
I also could have just missed an object too.
Yeah. Oh man. Do you know what you're could you share what you're controlling, and maybe there's a bit more info or can.
We're controlling the angle of the shooter, very similar to what Scott's talking about. But the encoders, we're just doing it by a reset basis of hitting a limit switch and resetting the value to 0 at the bottom, and then as it moves up, we just check the spark maxes. Well, we've got an encoder on there that's not absolute. We just check that, and so we're just controlling the position there. So we don't need a PIDF. But if in a use case that we probably would like that and the ability to do that.
Okay. Yeah, I mean, in that, if you're just kind of doing a similar thing, basically I would say like that. To get better than PID, you probably want like the profiled PID in WPIlib. There's a profiled PID controller, I believe it's called. And so really it's doing the work that Motion Magic would do, but you're doing it on the Rio instead of letting the motor controller do it. And so you're going to have the limitation of you can't get it quite as like clean or as quite that fast loop, but you'll still get a lot of the benefits. So that's worth looking at if you're trying to kind of take it up from the next level from PID controller on the Rio to trying to get it a little faster, basically.
Perfect. Thank you.
Yep. Yeah.
All right, let's do a last call for questions for Sam, and then let's use the last 10 minutes of our call if anybody has any other general questions, updates they want to share. Going once, going twice, questions for Sam? All right, big round of applause for Sam. Thank you very much, Sam. This was very informative. I admit that I am a PID novice, and every time my students want to do something with PID, I get very nervous about it. So maybe you've given me the confidence I need to help work with my students more.
Sure. And I know this was kind of dense, and so I do have like a dream of breaking this out into like a multi-part like video or YouTube video, but we'll see if that ever happens. But if there's ever people want to do another, like we can even just do like a control Q&A sometime. And I'm not like a world expert or something, but know some stuff anyway. I don't know.
You've inspired me to dig in too. I kind of look at this and I'm like, man, if we were only all just sitting around in a room and we had an arm that we could move and we could actually do the code together, that would be awesome. Maybe that's a good jumpstart idea for anyone who's looking for a jumpstart topic of put an arm on a control board with a Robo Rio and let's see how we tune it, control it. Yeah, very exciting. It's giving me ideas for off-season training things that we can develop too, and sort of in that same realm of how do we teach our kids PID for controlling elevators or arms or things like that. All right. Anybody have anything they want to share? Any type of announcements or anything? Update from how things went at your last regional, if you recently competed? Anything at all? I will share that we are still trying to get our robot put back together. We took so much damage, and actually it's making me very nervous about if we encounter the same damage at 10K, how we're ever going to get everything repaired before champs, and then worse, if we take damage at champs, which will probably take a lot more damage at champs, probably how we'd ever get it repaired before state. It's making me very nervous.
On that
Eric.
note, you
Oh.
saw what happened to DNA, which is at LSR. Our whole intake was shattered during finals, so that actually causes students to completely rebuild the robot from scratch. So, has damage been like that much for everyone else as well?
We actually broke our frame in half. The front half of our robot was disconnected from the back half of the robot at one point during competition.
Yeah, and for Noethic, it's funny because competition-wise, we've been mostly alright damage-wise, but we went to Shamrock Showdown, and we had a bit of an oopsie where we dropped the robot off a table. So we broke because we use a big gear, a rack and pinion to move our shooter. We bent both sides of that in the shooter, and one of the climbers. So very unfortunate, but it's been very lucky the damage that we've got, and we had spares from a practice spot. So repairs are coming great, but yeah.
Eric, you got something?
Yes. I'm wondering what people are using for their cameras for April tag, or how they're doing it.
KnightKrawler is using a Raspberry Pi with global shutter cameras we got from Amazon. I can probably tell you which ones here. They start with an A. Someone else may know this off the top of their head.
Right, but what are you using for software on that?
Oh, that's a great question. So we were using Photon Vision, and we were allowing Photon Vision to calculate position on the Pi. We are not going to do that anymore. We had lots and lots of problems at Lake Superior with Photon Vision, putting us at 0-0 on the field whenever it couldn't see an April tag. And I talked to several teams, and they were having similar issues. We didn't encounter this when we were practicing at home, but when we got to Lake Superior, if our cameras could not see an April tag, our path planner would start us in a position, and then you would see that 1 second in or half a second in, the robot's position in advantage scope would move over to 0-0, the corner of the field, and it would start trying to drive the path from over there, which is not where it was located. So we had to completely disable Photon Vision during autonomous so that we could drive pure odometry. Our plan is to step one is we're going to disable onboard position calculation with Photon Vision, instead just get out the raw April tag data. And then we are going to throw away any April tags that are not on the speaker, because we don't care about the other April tags for positioning. And then we're going to try to do some other filtering as well to discard. If we're too far away, we're not going to trust it. And we're going to say, no, we have to be within so many feet before we'll start trusting the April tags. I believe that's what Caleb, our programming captain, I think that's his current plan. He was also doing April tag with some type of a custom not Photon Vision image in the fall. And then he ran into an issue where the latest WPI version would not trust it because it wasn't an official image or something. And we switched to Photon Vision. I think that's what he told me. So we may, since we're going to be doing raw calculation, we may go back to his custom image he found and was using in November and December. All I know is that Caleb has said to me that the plan is that we're going to start doing manual filtering on the RoboRio position calculation.
What DNA is doing is with Photon Vision as well. And we're using actually on the robot side the Photon Pose estimator that just takes in the readings and then gives you an estimate, along with WPI libs. I think we're still using the WPI position estimator as well. We have found a similar situation where sometimes the robot likes to jump a few meters, So we are checking if our position is told to change by the April tags by more than like a meter or two, it ignores it, and that's worked quite well for us.
What kind of update rates and resolution are you using?
Our cameras are only getting about 20 frames a second with some lower resolution. It even drops sometimes too because we're running 2 cameras off of it.
Okay, so you're getting photon vision to run 2 cameras. I'm hearing there's some problems with that.
We haven't experienced any, but only one camera actually does the April tag checking. The other one is a mask to detect the note pieces. So
Right, that's what, as I said, we're having trouble with, from what my programmers tell me, that the photon vision isn't handling 2 cameras very well.
Eric, what are you running for cameras, and what are you running for a microprocessor?
Oh gosh, I'm not sure, but I'd have to have them tell you.
Okay.
They're running a coprocessor that's high speed, but they're trying to get it running today, and they just couldn't get the resolution or the update rates going.
Okay, so I pasted a link. It looks like Nate pasted it too. Those are the cameras that we're using, the ArduCam, the 120 frames per second mono global shutter. They're black and white, so you can't do game element detection with them. You can only do April tags with them. And we're also running them on an Orange Pi 5. So the Orange Pi 5 apparently has better throughput and processing power. We have 2 cameras, but we're only using one of them for April tags right now. We had a plan to use the back camera for positioning for the amp and for climbing to trap. But since we discovered, and we shared this, I think the week after Lake Superior, that the April tags are behind the polycarb on the trap, and if the lighting is above the field, you're looking up at an angle, and the lighting almost makes, well, at Lake Superior, it made it impossible to see the April tag because of the reflection off of the stadium lights. So we actually aren't using our back camera at all for April tag positioning. We may end up doing that for the amp. We'll see. But it's highly likely that we'll only be using one camera, the forward-facing camera, for shooting. So I can't speak to how many frames a second we're getting.
Yeah, as I said, they were having a lot of trouble today. They've been not getting the update rates they need.
Yeah, it's brutal. I mean, we spent, I don't know, 2 full Saturdays just grinding on whatever, trying to figure out how much to trust these different readings and how far away is like a good. And a lot of it just kind of comes down to when you're far away, you really can't trust your position that well. I think it's kind of where we landed. Throwing away the bad ones, and
they're doing well on X, but when they go at an angle on Y, it's hard to calibrate.
Yeah, I agree. We are seeing a lot more issues with April tags when we got to a real competition than we ever saw in the gym at home. And so I feel like as soon as we get our robot put back together, we're really hoping to spend a ton of time on autos and April tag positioning. And I think we'll be taking up every possible minute we can to try to figure out how to filter out the April tags. Ian's suggestion is a great one. I hadn't even considered looking at how far it was expecting you to jump. We did see, one of the things that we did see in the gym is that we would jump from when we were more than 15 feet away and on the edges of the field. Sometimes Advantage Scope would jump our robot all the way to the other side of the field and then all the way to the other side of the field. And that was because of how it draws that box on the April tag, and that box would sort of invert and it would jump you over the other side of the field. And so we have to work on filtering those things out.
Another thing that we're doing is we throw away all rotational resets from April tags because we don't want our robot to have our gyro reset by the April tag. We trust our gyro way more. And we also have a bit of code on the side of this. we just constantly, because the targets that you get from Photon Vision have a lot of like, this is the ID, this is the rotation, and all this other stuff, so that we can actually crunch the numbers. And when we were testing this out early in the build season, they spent like 2 weeks just playing with it.
That's news to me, Ian. I mean, I'm not very close to the programming this year, but the April takes can actually reset the rotation. Oh, I suppose that makes sense because it knows not only where you are, but supposedly what direction you're pointing. But how do you throw away the rotational resets?
We just don't allow it to reset our actual position, like tracker, like our odometry class just doesn't. It'll only update the X and Y coordinates from that.
Oh,
I see. So we get the X, Y, and theta in from the April tag, and we only use the X and Y.
Now I understand. Okay, that makes sense. I've only looked at that pose estimator code once or twice, so I will be passing this information on to Caleb. Thank you.
Yeah, we don't even actually use the tag. We don't even trust the position unless we can see two. That's kind of where we got. I mean, it's doable with one, but I just thought, I don't know, we're only using it to shoot pretty much, and when you shoot, you see two. Hopefully, rise of the shot blockers and all that. But yeah.
And I think that's probably where we're going to start. Is like I said, we're going to discard any tags that aren't speaker tags, and I think your suggestion is a good one of only use them if it's 3 and 4 and 7 and 8, whatever the numbers are. I think that's.
Are you using both of the April tags or just one of them for shooting?
We're using the Limelight, and so it has its whole it'll tell you where your location on the field is, and so basically what we're saying is don't trust that location unless you can see two.
I think the difference there, maybe Eric, where your question's going is that are you asking, are you pointing at the April tag? Because that was my first understanding before I looked at the code and understood what our programmers had done. My interpretation was a lot like retroreflective tape, where you aim at the tape, but in the quote unquote new way of doing things, use the April tag to update your robot's position, and then you use your robot's position, the odometry, to angle yourself towards the speaker.
Right. No, that's the expectation. They're just using one of the April tags rather than both of them. That's what.
Oh, I see.
They were talking about, that's why I was asking, they said that many people are using the newer Limelight very successfully, but they aren't available.
Mm.
That's what I was sort of curious.
Yeah, we are using it. It's hard because we were tuning code when we swapped them too, so we're not sure was it the hardware or the code that did it. But we're really happy with it now. It does work much better than the old Limelight 3 or whatever while we're moving. But it's a global shutter camera, so I mean, I don't know. I guess really where I'm going is I don't know if there's any special sauce in it really, but it did come in one nice package, so that was nice.
Okay, thanks.
I have another unrelated announcement for anyone who's part of who's a member of the Minnesota Robotics Coaches Association. The award links either went out today or should be coming out soon, so you can start nominating your students for all state awards and your team for the academic all state. So keep an eye out from your Coaches Association representative for that. You had to be a member of the Coaches Association by March 15th, and all the submissions are due on April 1st. So if you know that you've got a coach on your team who signed up for the membership, check with them and make sure that you get your all-star students nominated. Anybody else have any final announcements or anything? I will end my call with my typical plea of, just like Sam, you too can present a topic for the roundtable. So please consider signing up for a topic. You can always go to team2052.com/roundtable. Roundtable is all one word, all lowercase. And there you can see everything. You can sign up I think we're on our 41st now roundtable. Tonight was our 41st roundtable. You can see all of the replays on YouTube. You can sign up for the mailing list. You can sign up to host a topic like Sam did. Please do that so that I don't have to scramble last minute and come up with a topic. If you have something that you want to talk about, even if you're just looking for information, saying, hey, teach me how to do this, host a topic, create a slide deck saying, tell me how to do this, then tell me how to do that. Talon did that for wiring, and it was a fantastic presentation. And they didn't offer any tips or tricks. They asked everyone else for teach us how to do this, and it was so awesome. So you don't have to be an expert to host a topic. Just have a list of questions prepared and discussion points to talk about. All right. With that, I thank everyone for attending tonight, and I will see everyone next week. Have a good night.